Okay. Can we get started? All right. So welcome back to from the spring break. I hope you still had recollection of what we covered before spring break. So today I'm going to again begin with a slow pace, hopefully to catch up some of the material, and then we're going to resume full speed next time. Okay. So what we've been doing so far is that I think we presented what is a graphic model. We talked about how to do inference and learning on graphic model in exact sense, and then we figured out that for certain graphic models, such as a topic model, a easing model, they are so complicated that exact inference is impossible, right? So last time, I think we spent a good number of lectures on a technique called variational inference, right, which tells you how to perform an approximate inference on certain graphic models. So today we are going to start another, short sequence on a parallel technique, which is favored in another community, which is favored by statisticians, okay, in doing this kind of very complicated inference problem. They are known as the Monte Carlo methods. Okay. So Monte Carlo methods are, very, very different from the variational inference methods in their operation. But after we covered a few lectures, hopefully we can see at least from an operational level, they actually can be highly similar to each other, even though the theory is completely different. We're not going to, in this case, study complicated optimization formulation, outer approximation or inner approximation to the feasibility space, and the approximate loss function, and so on. So these are actually something which exactly turned many people, especially the statistician, away from variational inference method because they are complicated. On the other hand, these Monte Carlo methods are very, very simple to set up, and they have nice property, but they have some deficiencies. So now, hopefully, after these few lectures, we get a good sense about what they are. Okay. So again, this is the bigger picture of approximate inference, and today we're going to basically start our foray into these two domains. Okay, we've covered hopefully everything above that already. If you don't find yourself comfortable with all the materials above, you should come talk to us or go read the assignment, okay, in the class homepage. Right. So, what do we mean by sampling-based methods? So that actually gets down to the very question about why do we do inference? Okay, why do we do inference? And the inference usually amounts to, as we said, in a few examples, computing the likelihood of data, computing an approximation to the posterior probability of some random variables given evidences, and so on and so forth. Now let's ask even a deeper question. So once you have that, what do you use them for? Okay, and if you know what to, what they are used for, can we actually find an alternative way of achieving the same functionality? Okay, that's kind of a good question to ask. So here I suggest one example. For example, you have this maybe complicated distribution, which is a multivariate Gaussian. It might be simple, in your first sight, but let's pretend it to be very complicated, okay? And then the reason we want to have a distribution like this, in this case, actually it's very nice. It is in a closed form expression, is that we may want to use it to compute, certain values, okay, from that. For example, here, I want to compute the expectation of some function, okay, under this distribution. And then if you have this closed form expression, then we can bring in the p into here, and then you can do integral and compute everything. Right? So that's basically a very nice inference operation. But suppose I have a very complicated distribution. Let's draw an arbitrary one. So maybe let's draw just a one-dimensional distribution. I'm saying maybe we can have that highly multimodal, okay, to the point that this p of x does not necessarily even have a closed form expression. And I still want to ask you to compute certain, downstream, values or estimations, such as this expectation of arbitrary function defined on the random variable x. How do you do that? Right? So that's actually an interesting question to ask. What we see above is basically this question where we have a nice distribution where it's a Gaussian, you have a closed form. But we are more interested in this, or at least we expect that for any distribution, we actually don't know how to express them in closed form. We should be prepared that if they become very complicated like this. Right? So the sampling-based methods is a different approach. Instead of maintaining P of X, which is a closed form distribution, I'm going to maintain a collection of samples. Okay, let's call them XM. Okay, and I assume that these XM are drawn from this distribution. Okay, or if you get a lot of such XM, then their distribution, their cumulative density function, cumulative probabilistic function should actually follow this definition. Okay. And you can imagine you draw maybe many samples. Okay, maybe big N of samples. Okay, then based on the law of large numbers, okay, you can now replace this integral expectation of P of Fx by what? By basically plug in, okay, all the xm, okay, and you sum over all the m divided by n. Okay, so that's basically what we mean by a sample-based representation of distribution. Basically, you are going to have something like this. So you have a lot of points in here, a few points in here, many points in here, and a few points in here. So you can roughly see the density of my points is roughly aligned with the shape of this very complex density curve. Okay. And even though we don't know its exact expression, this sample itself tells such a complicated multimodality distribution. Okay? So that's basically what we mean by a sample-based distribution. So essentially, this guy is now replaced by a collection of samples. Okay? And the secret to guarantee this method still work is to make sure that your XM follows this distribution. Okay, so that's basically what we call a sampling or Monte Carlo-based methods. Monte Carlo is a nicer word because you basically are tossing dice in a certain way to get the sample from distribution. All right, so that's basically what I said. To make it more clean, I repeat the equation here, and you can prove that if these samples X are indeed drawn from the true distribution, then asymptotically it is exact, okay? And you can easily apply them to arbitrary models, okay? And this proof is trivial. We're not going to prove it, okay? You can kind of imagine that if you get infinite number of samples, then you are pretty much recovering the original density curve, and your integration is actually approximated by a summation of infinitesimal intervals. In each interval, you have just one dot point, right? All right, so this method sounds like very easy, but operationally, it might be challenging to realize. And here I raised a few questions, right? First is how to draw sample from a given distribution. So this operation may not be that trivial. So let me ask, how many of you have ever used a random number generator, like in MATLAB or anything? And what kind of function do you use typically? Random, which is a uniform distribution between 0 and 1, right? So that's a very nice random number generator. Have you used anything fancier than that? Draw a random number from some other distributions? From a Gaussian distribution. Okay, good. That's also implemented in MATLAB. Any other distribution you have tried before? Maybe multinomial. Okay. Good. Anything else? You may try gamma distribution, T distribution, if you are clever enough to Google and find some special implementation. Somewhere on Earth, there are people who implemented this very tricky sampler, allow you to draw very fancy distribution. But still, they are usually a one-dimensional T distribution, a one-dimensional gamma distribution, or some lower dimensional implementation. And again, in those cases, still, you have this luxury to assume that P of X is in closed form. You have an expression of that. Therefore, you can apply some kind of a tricky transformation from the uniform or from the Gaussian to those distributions. Okay. So, for example, I now give you a very arbitrary distribution, say a Bayesian network of many, many random variables, or maybe a Markov random field, or maybe something I don't even know what their forms are. I just know that they are represented by some training examples. Then the question is, how do we draw sample from there? Okay, so that's the question we need to ask today. And also, the second question is that even if you know how to create samples from those distributions, you will see very soon that not all the samples are equally good. Okay, many of them may be useless or maybe nearly useless, and you need to have a way to tell apart the useful ones from the useless ones. Okay, that's another challenge. And the third is again to challenge this claim asymptotically. Certainly this is for the theoreticians to show a nice property, but not for the practitioner to operate, because you cannot draw infinite samples. Right? Then how much sample is enough? Okay, so that we can stop and start our business. So we're going to study exactly these first two problems and touch a little bit on the third problem in the next few lectures. Okay, so I'm going to start, showing you the major ideas behind this type of method with a very simple example. Okay, and again to expose you some of the problems. You may see these examples already for some of you, but let's just go through them anyway for the sake of reviewing the material. So we have a Bayesian network, okay, of 5 random variables, and we can give name of them. Call this B, call this E, A, J, M. Okay, and I want to draw samples from this joint distribution. So the joint distribution basically will be XA all the way to XM, right? And therefore, I will basically define a sample to be a vector of a 5 dimension. Okay, and I want to draw, multiple samples. So M is my index. So how do we draw the first sample? Okay, I'm going to draw the first one. And here is the idea, which is kind of intuitive. Let's just, the Bayesian network defines a factored way of joint distribution, right? Which actually could make the definition of the joint quite rather easier. It's not going to be a big table of 5 entries. It's going to be a multiplication of all these little things. So we can draw sample like this. Let's look at the first random variable. It is following a distribution, a binary distribution of 0.001 versus 0.999. So I'm going to toss a coin there and draw value for this particular random variable. So what value are you most likely to get? Not having a burglary, because it's a rare event, right? So we're going to have a 0. So let's call this x1. Okay, so and these are, so I have a E, B, A, M, J, and let's start by B. So B, we get a 0. And then this E is also independent of that one. We're going to look at their table. And again, it is a very, very kind of a biased event. And we draw a sample. Most likely, it is also a 0, right? So now we are going to draw this. And this is a conditional distribution defined by this table, right? So how can we draw a sample from here? Anybody want to suggest? How can we draw a sample now from for alarm? Because we have this table here, right? There are 4 possible probabilities for this event to happen. How are you going to pivot into this table and use the right distribution to draw? Exactly. Based on the sample I draw from the parents, right? Or we already have a 0 here, a 0 here, therefore it should be false, false, it will be this one, right? And then we're going to now start drawing the value of this based on that distribution. Again, it's likely to be a 0, which is happening here, and so on. So you can basically traverse this network by sequentially drawing examples, okay, based on a local conditional distribution. And that guarantees you that the sample you draw as a whole, this one, is following your joint distribution. Okay, this is what we call a naive sampling. You just walk over the network and draw everything that you see. So sounds like quite easy, right? Any problems with that? Okay. So you may actually see this problem. Suppose that now I draw many samples. Here I have maybe 10 samples. I could go on, maybe go with 100 samples like this, which is pretty easy to implement. In fact, that's exactly why the statistician likes that. You don't need to be a computer scientist to implement this. This is pretty straightforward, right? But then when you start using this collection of samples to do calculation, you start to see problems. For example, now I want to compute the marginal probability of B, which is right over there, okay? And how should we do that? Well, you need to basically look at this B column, the marginal probability of B. You should, well, kind of see how, your events of B, divides across different options. And there are some problems. But maybe let's use a slightly easier example. Let's say this one. Let's do an inference problem of J given A not happening. Okay, J is here. He can do two things. I want to calculate the probability of the two things he could do, given that alarming here is set to 0. Okay, so how do we do that? You need to first examine all these columns with the J, and then you need to now pick the right row where A actually equals to 0, right? And so how many do we have? Actually, it's pretty good. Out of the 10 samples, we have most of them equal to 0, right? Therefore, you are going to, count the number of times this joint event happens, A equal to 0, and J being one way or the other, and then divided by the total number of times A equal to 0. And then you get this 1 over 9, 8 over 9 kind of probability of the events. Right? So pretty good. Now, suppose I want to do the other calculation. For example, I start to do this. I want to ask the probability of J given A equals to 1. What should you do? All right, you use the same strategy. You're going to look at this table, and you're going to look for rows where A equals to 1, right? In the 10 examples we had so far, there is only one event, following this kind of configuration. And then you are going to do the calculation, and you will actually arrive at a conclusion that this is, a extremely kind of biased distribution, where the probability of J equals to 0 is having a 0 probability, simply because such event isn't happening from your samples. Okay. So what's the moral from this example? It means that to enable inference, you need to have a lot of samples drawn in the previous way, so that all the possible events can be reasonably populated, so that you can start doing the simple count-based calculation, right? Which means that this sampling method is pretty ineffective, right? You need to actually draw a lot of samples, and at the end of the day, a few of them will be actually useful. All right, so that's basically opening a need for developing actually fancier methods. In fact, that's even in the case where the sample can be easily generated. What if the sample cannot be easily generated in that way? Right? So here, let's start with a roadmap. Here are the 5 or 4 major techniques now people use to do Monte Carlo methods sampling. And the first one is direct sampling. We've seen it already, right? It is very difficult to populate a high-dimensional state space. Okay, and we need to ask whether it is necessary to populate a high-dimensional space if we actually know, certain inference tasks to be more often than others. So we're going to now gradually actually move up the power of the sampling methods by studying this sequence of approaches. And let's do the rejection sampling first. Okay. All right. So rejection sampling is to first address the question of what if I'm given a complicated distribution, okay, where I cannot draw a sample from. For example, I have such a very generic exponential family distribution, or a Gibbs distribution where you have a product of potentials normalized by a constant. Okay, and so this is very difficult to sample. This pi of x for many reasons. Okay. First, the simple reason will be, this form may be a very, complicated one that you have never seen in your library. Maybe, it is, I don't know. I don't know even how to call it. Maybe a very high-dimensional Ising model. That's already simple. What if I have arbitrary, tabular potential for that model so that I don't even have a name for this distribution? Okay. And therefore, drawing sample from this guy can be difficult. And then, it can be even more difficult that even if you draw the sample, you may not be able to figure out how to evaluate this sample under this distribution, because here, this distribution requires a knowledge of the value of the normalization constant. And we know that for many distributions, we are more interested in this part, which is our design of the potential functions or of the energy function so far. We want to stay away from that partition function because its only value is to make sure that my numbers are normalizable to 1. But otherwise, it is not really increasing any power of my modeling, right? So, to evaluate the probability of a sample under distribution, I have to know that. Again, that's another question. So here I have a proposal. Instead of drawing samples from this pi, which is difficult to sample and difficult to evaluate, okay, we're going to sample from a simpler distribution Q, very, very mysterious. Q can be a very simple distribution of anything that you can find out from your library, maybe a Gaussian distribution. Just do it, okay? And then we also assume that even though this pi of x is hard to evaluate, but this pi prime of x is easy to evaluate. Can you see that point? Because without the normalization constant, the pi prime of x is just a bunch of potential functions. You just plug in a number and you get the value, right? Without normalizing. So evaluating on the unnormalized distribution is actually trivial. Okay, so we assume that can happen. Okay, so the idea about the rejection sampling is the following. I'm going to draw a sample from Q of x, which is supposed to be easy. Okay, and then I'm going to now hold off a little bit and do a test where I'm using, pi, prime over a k times Q of x, and of course I need to set the k such that this number is always between 0 and 1. Okay, and then I'm going to accept this sample with a probability determined by this quantity. Okay, so I claim that the sample you got as a result of this two-step thing is going to be following the original distribution you got from pi of x. Can you actually show me a simple idea proving this claim is true? It's kind of a very strong claim, right? And the procedure is rather simple. I use an arbitrary distribution Q, and I do a second step test of acceptance. Then I claim that the distribution is actually following the original distribution that I couldn't sample from. How that can happen? All right. Let's maybe do some little calculation. I'm going to show you a simple technique to do this kind of proof that you will probably use down the road for similar kind of examinations. So now we have a P of x. How about we just examine the probability of P of x star? Okay, this is the sample we generate using these two steps. What is the probability of that? Well, this guy has to be proportional to Q of x because the x star is drawn from Q of x, right? For sure. And then it is also, subject to another step of scrutiny, which basically amounts to a test, right? Whether to accept a sample or not based on a binary test with probability determined by pi prime of x. Actually, by the way, I need to plug in the star here, divided by k of q of x star. Right? So basically, the probability of x star must be proportional to these two, to this one, which is a product of two probabilities. Right? And of course, to make them, to turn the proportional sign into an equality sign, I have to properly normalize it. Right? That's all correct, right? So now let's do some very trivial kind of manipulation. This guy should cancel each other, right? This guy should cancel each other. This k constant can cancel from top to bottom because they are constantly can be taken out of the integration sign. And interestingly, what's left is basically this guy. Right? Okay. So this is basically the probability of what? Of the original distribution, right? Right? So this is by definition that guy. Therefore, what we are sampling from is actually from the true distribution. Okay. So that's basically the trick. You are going to introduce an auxiliary distribution Q, which is very easy to sample, such as a Gaussian. And then you're going to do another test, okay? And then we're going to actually recover sample from the original distribution. So sounds like too good to be true, right? How come, without doing anything non-trivial, we already, overcome this very, very, difficult question of sampling from arbitrarily difficult distributions? So any question that you can spot from this whole reasoning, this whole process? What do we lose as a result of this procedure? So we gain by now able to create sample x star from that complex distribution. That's what we gained by using a simple procedure. What do we pay for that? That could be a very subtle question. Yes, please.
There's two things. One, you have to figure out this k constant. And another is that if q is very different, k will be large, and you're going to reject a lot of your samples.
Good point. So the key issue is that, so k, of course, need to be figured out. Well, it's kind of, at least not impossible to figure it out because all you need to make sure is that you can take a derivative of that so that you can know the extreme point of the density of the original density and make sure that even over there, your Q is bigger than that, right? It's kind of doable, at least, although it could be tricky. But the real question that you raise is the following, right? This step, we don't actually know how good it is. What if I end up rejecting 90% or 99% of the samples, right? Then out of 100 things I draw, I may get one useful sample. And this can happen, right? For example, I have, again, a fancy distribution like that, right? And certainly if let me draw with another color. So suppose that my Q is like that. It is a legitimate Q. Let me first ask you, is this Q legitimate? Or maybe I can even do this Q. Is this legitimate? Well, if I got a sample from here, then I'm going to have that test statistic to be something quite strange, right? Oh, by the way, this curve is not the p, it's actually the pi prime, okay? It's evaluable, okay? But still, you are going to get something which is greater than 1, right? Which creates a invalid issue. I have to basically turn the Q such that they should be always on top of the prenormalized density function, right? And then the implication of that is when you use this Q to draw sample and use this to do the test of acceptance, then all the space that is above the true prenormalized density and below your proposal distribution will be actually correspond to the mass of probability that you're going to reject the samples. All right? Therefore, here you can imagine you have a huge chance of, making the sample drawing this way useless. And here I have another illustration of that, right? And I can give you another example of showing how extreme this can be. By the way, I reproduced the derivation in here just to make things clean. And here, of course, this is a very artificial example, but I can tell you, give you an impression about how serious this problem can be. Okay, the example is kind of awkward, but bear with me for the sake of a mathematical argument. Let's say I want to draw a distribution. This is a Gaussian distribution, okay, of d dimension. Of course, in here, I'm not talking about a two-dimensional Gaussian distribution or one-dimensional. I'm going to make my dimension to be rather high, let's say 1,000. And don't ask me why. For some reason, I want to use a different Gaussian to sample this Gaussian. Okay, just for the sake of argument, even though it's not necessary. But I'm going to use a slightly different Gaussian from the true one. Okay, the difference is rather small. They will be having the same mean. Okay, they use the same mu. Their variance, okay, is a little bit different. This one, theta q, is greater than the other one by just 1%. In a sense, you have this solid curve to be the true density, and my dotted curve is the proposal density. Okay, just these two differences. And you can now calculate the Q, the K, basically. So how to calculate the K? K basically should be, the extremal point of the density function, and then you compare, the magnitude of that P, or prenormalized P, under the two distributions, right? And you can actually show to yourself that because the definition of the Gaussian is basically, epsilon d over something, and then 2 pi 1 over 1 and plus the exponential form. Somehow, when you do the comparison, you will figure out that the K actually has to be equal to the ratio between the two variance to the power of d. Okay, and when d equals to 1,000, it will actually produce a very, very, tiny number. Okay, so that the K can actually make one of the proposal this lower than the original distribution, or this higher than the original, depending on how you say it. Right? So there will be a huge waste of sample even for a very simple distribution, especially in high-dimensional space. Okay, so that's giving you a kind of a geometric picture. What you see in the lower dimensional space is usually a very benign kind of picture, and in a high-dimensional space, some slight variation will create a huge space of possible variabilities or flexibility that you cannot cover, and therefore, you can really get into trouble, with that very high-dimensional void state space. And then, you can imagine some way to mitigate this, right? And one way, of course, is to do something called a adaptive rejection sampling. I'm not going to cover the details because this is a very, very specialized technique on only lower dimensional problems where, you just imagine an envelope. Okay, this Q density function is going to be a combination of multiple such envelope functions to make sure that you can create a tighter kind of cover of the true distribution. But again, this technique is not very, very generic because in the high dimensional space, you need to have a lot of such half space to actually generate a good envelope, right? And in fact, you don't even visualize the whole thing. Therefore, you have to go purely analytical to make sure that all the envelopes are correctly positioned. So that's a rejection sampling, all right? Okay, so rejection sampling is not it's okay, but it's not very good because we're going to reject a lot of potential useful examples, right? Just because a poor proposal. So what's next? So here is a next step. We call them importance sampling. There are two versions of importance sampling, and I'm going to tell you the simpler one first, the unnormalized one. So again, the key point is that we shouldn't really reject any samples because if we reject them, you cannot use them. If you regret, there's no one to find. You get a sample, you don't store it, and it's gone, right? So ideally, we want to really make use of every sample we generated. Maybe we use them differentially. We just don't use a unweighted sum of any quantity over all samples. We may want to use them more smartly. So this is the idea. So now suppose again we can sample from this singular distribution, and also we can evaluate from a pre-normalized P, okay, and then how about we do the following? Okay, so instead of rejecting the sample using this formula, we are going to now for every example create a weight. Okay. So basically, we're going to draw the XM from a Q distribution, okay, and we have M equal to 1 to M, okay. Then for every of them, we're going to compute a weight of M, which is defined by P of X and the Q of X, M, okay. And therefore, my collection of samples is actually a tuple of two elements. Okay, one is the XM and the other is the WM. Okay, and then the way I'm going to use it is to always use a weighted sum of sample-based quantity. Okay, so that's here. Okay, so that's basically making use of every sample, and if, for example, if everything goes well, you may imagine at least I don't waste any sample, right? And of course, you can argue that I'm still implicitly wasting because what if I have a lot of samples with small weights? But that's a different issue we can worry about later. At least the weights are not zero in this case. Okay. All right. So looks and again here are the proof of why that method is correct, right? So originally I want to produce this, and this is actually a way to motivate different sampling methods. So your original expectation, you introduce some auxiliary terms here, and therefore you are now creating a chance for Q, and then this is almost like this quantity is now averaged over the Q distribution instead of the original quantity averaged over the P distribution. In this case, you treat this whole thing as a target, and then you replace this expectation with a summation over samples. Therefore, you replace the Q integral with samples from Q, and then plug in the samples into this first term. Okay? And that basically shows the correctness of this algorithm. Now, what problem you can imagine for this technique? What's that?
You need to calculate PXI.
I need to calculate the P of Xi, right? Yeah, and again, I just said this is not very possible. In fact, here I have to use the unnormalized version because I have to use P as it is and assume that I can actually compute P. And this is not always possible, right, for complete distribution. So the question will be, how do we do this? And in fact, we probably don't know. Okay. So unnormalized importance sampling is good, but it has a limitation because it requires you to know how to evaluate every sample from the original distribution. Okay, so what next? Any ideas about how we can overcome this? Okay, so here let's basically getting trickier and trickier. Okay, So now suppose that we, after all, cannot compute the P. And again, we can assume that we only evaluate P prime, which is the pi prime before, by the way. There are some notational kind of confusion, but you should hopefully understand from the context. Here I have, again, a pre-normalized distribution. Okay? And you can imagine this one is the product of potentials and so on. And they can be evaluated. Okay? And then this alpha is what? Alpha is the partition function, right? And we don't know. And what if we actually figure out a way of computing that in a simpler fashion? Okay, so that's kind of the challenge. So let's go through the following thing. Okay, we can actually get around this nominal constant, using the following idea. We define the ratio, okay, R, which is the ratio between the pre-normalized P versus the proposal distribution. So this is a pre-normalized P, called P prime, okay, and we can actually try to study this quantity a little bit more. For example, let's study the expectation of this R under the proposal distribution, okay, and so we're plugging in this and taking integral over that, okay, and this guy we know how to calculate, right? Because it is basically, a sample mean, right, of the R. Basically, this is what? This is R of M sum over that, something like that, right? But on the other hand, this quantity can be further simplified if you actually get rid of cancel this 2Q. You actually get this part, okay, and you actually found that this expectation, okay, of the ratio with respect to Q distribution actually equals to that nominal constant. Isn't that amazing? Okay, so this actually gets now to this. We have R of X, Q of X, D of X. So by definition, alpha equals to this guy. And therefore, alpha can actually be calculated based on samples. You cannot calculate in exact form because this particular integral is not easy to do in exact form, but you can always replace a Q-driven expectation by samples from Q. Okay, so now we actually get a chance to deal with this alpha, right? And therefore, we can now do the following. The new, expectation, okay, based on this, we call a normalized importance sampling, can go like following, okay. So we're going to, let me first tell the procedure, okay. We're going to do this. We get M first from Q, okay. We're going to get maybe n of them, okay, and therefore we get x1 all the way to xn, okay, and then we're going to compute the alpha, okay, from what? Actually, here we also have the R of 1 and the R of m, right? And then we're going to compute the alpha by basically performing a sum over m. Okay? And then we're going to now use this alpha to renormalize the R's. And the procedure goes like this. You can naturally follow from distribution. So we're computing the expectation of this under a true distribution. And true distribution is not manageable. We introduce the auxiliary Q, okay, and then we also do a little bit of rewriting of the P to make explicit two components. One is the P prime, the pre-normalized target distribution, and its nominal constant, okay. So now for this part, how do we do that? Right, so this is R, right? And this alpha is what we get from here. It is this guy, right? So therefore, now you have these two things. On the upstairs, you have a Q-driven expectation over R and F. And in here, you have a Q-driven distribution expectation over R only, right? And this guy, again, can be replaced by a sample-based summation, right? So you are going to replace both upstairs and downstairs with a sample-based summation. And now things become clear. Once you are in here, this part corresponds to a normalized form of the R, right? They are all the R's, and then each of them will be divided by the same thing, which is the sum of all the R's. Okay, that means they are normalized R. And that's why we say, at the end of the day, you are going to get a representation of samples, their weights, and their total, value for normalization, right? So that's why we call it a normalized importance sampling. And at the end of the day, again, you are now going to use these weights. Okay, these weights is different from the previous weights. These are the normalized weights, and to compute a expectation of arbitrary functions defined over variables. Any questions? Kind of magic, but you can see that this by manipulating, a proposal distribution Q, and then by further manipulating the sample from Q, with respect to the true target, the way how the sample can be back and forth reused. At the end of the day, you can circumvent a number of seemingly, tricky difficulties, such as computing normalized constant and so on. Right? Questions so far? All right. Good. So this is a interesting slide. Now we have two ways of doing the importance sampling. One is normalized, the other is unnormalized. And what's the, asymptotically, what's the difference between them? Okay, and which one is better? Let's ask the following: which one is better? Normalized versus unnormalized. So I think this question is kind of unfair because better means a lot of different things. Now let's see. Suppose that you really, really want to implement your algorithm for a arbitrary target distribution P, and you don't know how to, compute or evaluate the P. Then which one is better? No question, this one is better because that's exactly telling you how to do that, right? But now I ask, if you actually know how to evaluate P, which one is better? Why? Mm-hmm.
You're not approximating P by samples anymore.
No, I'm still approximating. It's always approximating anything by sample, right?
But evaluating P itself.
Okay. Evaluating P is okay. But in the second step, I don't even evaluate P, right? I'm not approximating anything. Right. You are getting there, but the argument could be a little bit more sophisticated. Okay. Because here, everything is based on approximation. We are drawing samples from something, so it is not a closed form expression anymore, right? It is really about the asymptotics, right? If you do the same thing n times and infinite times, and you want to ask, am I getting things right? Then you will see there are two different possible outcomes. That's basically the sample bias and the variance argument that we want to, we probably can recall from early lectures. So here are some interesting thoughts. Suppose that I'm allowed to only, draw one sample, okay? So x, I want to compute the expectation of x. And of course, if you are impossibly drawing only one sample, but just say fail. But for the sake of argument, let's say just one. Okay, this is only x. And I'm going to do this same thing n times, infinite times. Right? So I'm going to compute whether my results is going to converge. This is a little bit different than doing this same calculation based on many, many samples. Then you sum them together. This is that you estimate this based on one sample, but you estimate many, many times. Okay, and then we see whether they give you the same result or not. So in here, we plug in X, which is the sample from the original, the Q distribution. Okay, and so we can basically say, well, this guy equals to f of x and wx and q and dx. That's by definition, right? And then I'm going to introduce the definition of W. This is the unweighted, unnormalized W, remember. It is going to be the true P divided by the Q and times Q of X, right? And of course, these two cancel. Therefore, I'm going to get what? F over Px, which is actually E of Px, right? So just by this, just a very simple derivation, you will see that this expectation actually is converging to the true expectation, right? And this equality holds because I did the whole thing infinite times. Therefore, they are equal, right? So we call this a unbiased estimator. Okay. Now let's look at the second one. This is actually a very subtle difference. The second one is based on, let's say, first sample n times, compute a normalizer, and then reuse these n samples in a normalized fashion to compute this, right? Therefore, I need to basically augment this R a little bit. And for the sake of argument, let's make just one sample. You can do two samples as well, which makes the derivation a little bit different, but by nature they are the same. One sample, then basically this one need to be normalized with that one by itself, right? And then by definition, you have what? You have this times what? 1, right? And then Q of X dx, right? Which gets you to the expectation of the F under Q, which is, of course, different from the one under P. Okay. And, of course, you can try this one may be artificial, but you can try that M equal to whatever number, as long as it's finite. And you will see that it is, always a biased distribution. Okay. So in that sense, as some of the people here already suggested, intuitively, if you can actually afford to compute this W truly, then you use this unnormalized one because it is giving you the exact estimate and it is unbiased. But the reality that you cannot do that, then this will give you a better thing. But on the other hand, variance is not the only thing we discuss. Bias is not the only thing we concern in sampling procedure. There's also an issue about variance. One can actually show that the variance of the normalized important sampler is usually much lower, okay, than the unnormalized one. Okay, so that's something that's you need to take into account. All right, and sometimes, of course, we know that this normalized one is crucial for any distributions that you can only evaluate P of X, but not a P of P prime of X, not a P prime PX themselves. Right. All right. So, question so far, we've covered now 3 samplers: rejection sampler, and 2 types of important sampler. Okay. And maybe it's time to stop and look at a instance, how that can be practiced in reality. Let's say maybe something you probably heard about, called the likelihood weighting, which is a particular form of important sampling. And here is just a live example for you to, get a real sense about what you're actually trying to do. So I have a true distribution in here. Again, this is a fancy Bayesian network. And say I have a few evidences already. Maybe I can set this to be the evidence already. I see them already. Okay, and I want to sample from P. Let's maybe giving some index 1, 2, 3, 4, 5 maybe. And I want to basically compute the P of X1, X4, and x5 given x3 and x2. Okay, so that's basically my goal. And what does this distribution correspond to? This corresponds to a pre-normalized one, which is p of x1, x4, x5 plus some evidence, right? Divided by p of the evidence, right? So you can kind of already imagine that this resembles a pre-normalized distribution plus the normalization constant, the partition function, right? And maybe you don't want to compute this guy for whatever reason, right? Okay, so then how can we use the important sampling idea to sample that? For example, we need to get a Q distribution, right? So what could be a good Q for that? Any suggestion? The Q will be defined on x1 and x4 and x5 only, right? So here I actually have a graph already showing you that. Because you already observed these evidences already, let's just set them to be constant. So I actually you can see that I changed the whole thing already. So this guy will be set to 0, 1 because it is a deterministic value. And this guy is also set to 0, 1 because it is also deterministic. It's happening already, and it doesn't depend on any parents or anything, right? So my Q distribution could simply be, P of now x1 times P of x4 given x3 equals to what? Equals to, I don't know, evidence. I just call them evidence. And times P of x5 times x2 equal to evidence, right? And that's basically my Q distribution. And then how do you sample from this Q distribution? I'm trying to, somehow walk you into an exercise. And here I already proposed the target, the proposal, and now I ask you to start sampling. How do you sample from Q? Anyone want to give it a try? What do we sample actually, first of all? We need to first understand what I'm trying to do. We're trying to sample a triplet of xi, x4, and x5, right? From this Q, right? And the Q is defined now in this way. How do we sample?
You can generate a random number between 0 and 1, and for each of these individual probabilities in that product, you generate a random sample from those probability distributions and then take the product.
Okay, I think what you say is this. I'm going to generate P of x1 directly from P of x1. I'm going to generate x4 directly from P of x4 given x3. And I'm going to generate x5 directly from P of x5 given x2. Right? You may wonder what progress I made. Well, I made a lot of progress because sampling from here is going to be very hard. But sampling from here is trivial. Right? All I need to do is look at a very simple table. I don't need to do any inference on conditional probabilities of these three given the other two. Right? And then after I do this, what should we do next? It's kind of here already. I now need to compute the weights. Right? The pre-normalized weights is this guy divided by this guy. Basically, I need to now plug in these three values into that distribution and compute its likelihood under Q, right? And I'm going to compare. So what is this W correspond to? Are they normalized weights or unnormalized weight? Mm-hmm. Mm-hmm.
W itself is unnormalized.
Yeah, it is unnormalized. So you need to then do another step to normalize the W's. Okay, in fact, it is safer to always normalize W. If it is normalized and you do normalization again, it doesn't change anything, right? So that's usually what I would recommend to do. So at the end of the day, you start to get these samples of these 3 random variables, and together with their weights, with their normalized weights, as a set of true samples that you can take down to use for other purposes. Maybe let me just go funny and ask you what other purposes I can do. Like with this sample, what kind of inference I can do. Go back to that burglary network example I just discussed at the beginning of the lecture. Right? For example, can you now ask the likelihood of a letter given intelligence? Right? That's a conditional probability. What do you do? Well, you basically just examine that in these samples, how many times that sample is corresponding to a condition where intelligence is set to the value that you want to see, and compute how many times they occurred, right? And you can tell yourself that in this case, the wasteful sample may be less, may be fewer. Why? Because the way you draw the proposal is already clamping your sample to the evidence. You're not going to see a lot of samples which is not agreeing with your evidence, right? Remember in our previous examples, we want to have the conditional probability of J given B equal to 1, and we look at the table, there are just 1 row equal to 1. And in this case, your sample is going to be generated by already clamping the thing equal to your evidence. Therefore, you're not going to run into that problem. Of course, these samples may not be equally, shouldn't be weighted the same as the sample you generated in earlier approach. That's why you need all this reweighting scheme as well. But still, you have a much more effective use of the samples. All right, so this is a pseudocode to perform this likelihood weighting algorithm. Now let's, okay, this is not interesting anymore. And let's do the last algorithm. Hopefully we can cover today. I actually have last 2 algorithms, but I'm going to probably only have time to cover this one. The problem of important sampling is that it really still depends on, the quality of the Q very, very heavily. Okay, so let me give you this kind of a weird scenario. So this is kind of the funny exercise I want you to do. So keep inventing the new methods and then keep beating yourself and telling you it is no good and then move forward. But it's very hard even for myself to jump directly into that final kind of solution without seeing all these intermediate, sometimes useless steps. So here is how I found the problem with this important sampling procedure. Again, I'm going to use a kind of an extreme example. Okay, maybe I draw it here. This graph is good, but it's not extreme enough yet. I need to draw it even a more extreme one. So let's say my target distribution is like that. Okay, I'm going to make it extremely extreme. Okay, so this is my target distribution. And I want to, and this is P. Let's forget about it's normalizable, not normalizable. The same problem exists in both cases. And how can we actually draw a sample from that? By the way, here, imagine this one is really touching the line almost. Okay, I just want to make sure it is very, very small. It is not as high as here. And I want to do a proposal, maybe Q. And, I can have this proposal. Okay, not bad, right? So at least if I generate samples from this proposal, maybe, of course, more samples will be coming from here, right? And then I'm going to generate a weight, which is what? Which is P over Q, right? So in this case, P is okay. It is, not infinitesimal, right? And the Q, of course, is very big. But still, I can get a reasonable weights. Not for the points in here, because now the Q, actually here is still good, right? Because, but on the other hand, here, the Q is P is very big, but the Q is very small, which means that in this space where you're supposed to see a lot of mass, you unfortunately don't get a lot of samples because your proposal is a mismatch, right? That's one problem. There is yet another problem which can be even more, troublesome. Let me change a color. How about I use green here? So how about this guy? Because I don't actually see the shape of the true distribution. And remember, we are doing a high-dimensional statistics. We actually don't see the shape of density. We have to guess. What if we are unfortunate enough to guess this one? Like this Q is in here. And I need to draw sample from Q. And my sample are mostly coming from here. A lot of samples. And maybe a few samples from here. Almost no sample from here. Okay? So what will happen in this case? We're going to still compute a P over Q for the weights, or maybe even normalize it. What do we get? What's that?
Most of the points are not qualified.
Well, what do you mean by not qualified?
We get a lot of samples with very high weights.
Yeah.
With a lot of sample what?
With very high weights.
With very low weights. Yeah, but they will be normalized. Right? If I have all the samples to be weighted 0.0005 and I have 100 of them, I will renormalize them. I can still turn them to be, a pretty decent number, right?
The samples are not a true representation.
Mm-hmm.
The samples are not a true representation of Q.
Yeah, so there are a lot of issues in here, in fact, Yeah, so the weights being small is one problem which could be correctable if you are renormalizing them. But again, renormalizing is already a cost, right? It is a problem. The worst thing is that you miss a lot of interesting density region, okay, in here. And basically the samples are not representative enough. Okay, so that's something you can conclude at hindsight. When you see this, you conclude that it is not representative enough. But the truth is that can you actually even discover this flaw or not? That's actually the problem. Usually when you do sampling, when do you discover a problem? Okay, or when do you converge and decide not to sample anymore? Usually it's like I sample, and I see nothing change. That's actually a very high level, good kind of wisdom on stopping, right? If nothing is changing, I'm going to stop. Meaning that if the sampling trace is of low variance, I'm going to stop. Okay? And if you look at this example, you will be in a very strange scenario where you will get all these samples a lot under this proposal Q. And they will be uniformly or universally getting low weights, and they don't change a lot either. It looks like you are doing okay. Okay? And if you compute whatever estimate out of these samples, X and weights, they don't change. But even though they're not changing, they are not landed in the right density kind of the mass space that you are supposed to be landed. Right. So that's actually the problem with the important sampling, weighted or unweighted important sampling, which is very hard to correct. You cannot touch such a problem. Okay. And here so my graph here is meant to show that, but I said it's not extreme enough. This one actually is better. Right? So so that's actually the problem. We cannot really detect whether our sample are representative enough because we don't have a way to diagnose the variance, okay, in those samples. So for that, we're going to try another method called weighted resampling, which is using this idea. So not only we're going to compute the weights of every example, we're going to actually use these weights to redraw samples from the samples. Okay, so the idea, do I have something here? Yeah, okay, I have something here. Let's draw samples from Q. Okay, draw this many. Change back to red. Okay, and then I'm going to redo the weights. Okay, I'll compute the weights based on the usual procedure. And then I'm going to now subsample X again from these N samples using these weights and the sample weight replacement. Okay, in fact, I should say here I'm doing N prime. Okay, actually, no, for n prime times. So I'm going to get a sample of a 1 all the way to n prime. And n prime should be way, way larger than n. Do you see the point? Right? So I have a weighted set of samples, n, and I also have a distribution over the n's samples. I'm going to use that distribution to redraw samples from this distribution, which means that some sample can be reproduced twice or multiple times. Okay, some actually can be ignored in the second round of sampling. Okay, so this is called the weighted resampling. So at the end of the day, I'm going to use this, okay, as my representative of the distribution, and again with their weights in here. See that? All right. So and this is a very, very important procedure used in a well-known sampler called the particle filtering. And I'm going to hopefully have time to present the math today, and if not, revisit next time. Okay. So the goal is to, again, do a sequential sampling of some fancy distribution. Again, this idea is used in many different settings, but this example is the best way to represent, to manifest that kind of idea. So our goal is to produce a distribution of this guy conditioning on this guy. Yeah?
So px here is again normalized or unnormalized?
What's that? Where?
The px?
It doesn't matter. Yeah, it doesn't matter. I'm not talking about another type of problem already. Remember I said in the previous lecture that, previous slide, that no matter you normalize or non-normalize it, what I'm talking about is a different issue. The sample is not representative enough in terms of their variance. Okay, yeah, you can do either way, whatever good for you. Okay. All right, so this guy, that's my goal, and how can we generate a sample from here? And again, doing this sampling directly is kind of hard because you don't have a closed form expression of the distribution of a single random variable given the entire thing, other than you just do your exact inference first. But the whole point of doing sampling is to avoid doing inference at all, right? So here is a sketch of an algorithm called particle filtering, which is a very interesting, application or practice of that weighted resampling idea, which I'd like to spend a few more minutes to discuss the details. So first, our starting point is, again, this is an algorithm made for online inference, meaning that at every time point, you are going to produce the prediction of this state based on the new samples you get. For example, the new example you get here, and also based on the previous examples. You're not supposed to redo the whole thing from ground zero, and redo the whole inference. Okay. So at the time t, we have this guy. Okay, the conditional of xt given the sequence of y of 1 to t. Okay, and now let's see how can we start from here to produce a p of xt plus 1 given y1 to t plus 1. That is our goal. Okay. All right. So here are some kind of interesting derivations. I want you to just understand why I come from this step to this step. First of all, the importance of this rewriting is that now I can use. Are you familiar? Hopefully you are familiar with this. This is more like a sample-based representation. This guy can be now expressed by a two-component. One is yes, so it is a normalized form of that, and here I can have now different ways of representing this using samples, and we can later assume that samples from these two steps can be easier than coming from here. So let's see how can we actually get this step first. So we have a conditional of x given the entire y sequence, and I will do some rewriting, and the denominator, the numerator actually corresponds to p of xt, and yt times y1 to t minus 1 divided by what? Do you agree with this? I just want to rewrite this one into this. Okay? And then this guy can be further rewritten as p of xt given y1 to t minus 1 and times yt and xt and y1 to t minus 1. You see how to go from here to here? Just a chain rule, right? And from here, if you use the conditional independence property in a chain graphic model, you will see that the last term actually equals to p of yt given xt only. And everything else becomes deseparated, right? And that's why we get this term. And likewise, you can do the same derivation on the denominator, and that gets you this part. Okay, so that's one thing. And now let's see. First of all, let's look at this part. Okay, what if we treat we define little r, okay, to be the normalized form of this guy. Okay, we basically define a weight, okay, based on a sample representation of this normalized distribution of p of y given x. Okay, and then we basically now can decompose this distribution, the starting point distribution, as this guy weighted by these weights. Okay, therefore, to represent this, we only need to draw sample from that distribution, okay, and then compute the weight based on this formula. Okay, so that's first the starting point. We start from this distribution, and this distribution is now represented by a sample and their weights. Okay, and the derivation is now done in here. Okay, and our goal is to figure out how to use this to generate samples, okay, for t plus 1 and w plus 1. That's basically our goal. See that? Okay. I found the time is up. Do you want to see it now or see next class? Maybe I can spend 2 more minutes, and then we can finish the whole thing next time. So it actually, to move from this set of samples to the new set of samples, you need 2 steps. The first step is called time updates, which basically amounts to basically figuring out this guy, okay, for the next time step. The xt plus 1 given the sequence up to the last time point. And by definition, you can expand them into this form, okay? And in this form, what you see is this term, which is a new guy, and this term, which is what? Is here, right? So you have a sample expression of this already. So you replace them with sample. You bring in the sample, okay, which actually includes the sample itself and also their weights. Therefore, we can express this distribution by a weighted sum of this term, okay? And remember now, the xt is replaced now by samples. It's no longer the true x, okay? And every sample is weighted. And if you look at the form of this, it's almost like a mixture model, okay? A mixture of this component weighted by this. And you're going to draw sample from here. And we know how to draw sample from a mixture model. Very easy, right? And then once you have a sample from this guy, we're going to now move 1 step forward. This is our target distribution of a t plus 1 given y t plus 1, 1 to t plus 1. And that's by definition, defined by this guy, which is, a product of this predictive distribution of xt plus 1 from y1 to t times a emission probability at xt plus 1. Okay? And so here we know this guy already, right? This guy is actually what we produced in here. And what is this guy? Look at this again, right? This is, again, a new kind of set of weights, okay, of samples coming from here. Okay? Therefore, what you do is that you draw sample now from here, from this mixture distribution, and then reweight them based on this procedure. Okay? So to put things together, you start from this distribution, which is xt given y1 to t, and here I use the ball to express this set of samples. So these are the samples which are weighted. Therefore, you have samples here, 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 and they have different size because they are weighted already. Okay? And then you are going to use this to generate samples for xt plus 1 given yt. This is a predictive distribution of the last sequence to the new state, and you generate samples from here. Okay? Therefore, you generate a bunch of unweighted samples, okay, which is in here. Okay? And then you are going to now also compute a new set of weights, okay, based on this R function. And these are the new weights. Okay? And then these are the new sample, these are the new weights. When you combine the new sample with the new weights, you now get a newly weighted set of samples, which now represents the new set of distribution in here. Okay? So that's how you get from here to here. Okay? Starting from a weighted sample, generate an unweighted sample, compute the new weights, and then reweight it to get the newly reweighted samples. Okay? And you can go this on and on again for every time step. That's why it's called an online algorithm. Every time, in the time step, you just do this computation based on the current evidence, okay, which is the yt plus 1 in here to generate new weights, and then your sample are coming from the older distribution in the previous version. Okay? All right, so this is called the particle filtering, and next time, hopefully, we're going to review it again, and then we're going to see how it can be used for fancier distributions, and then we're going to talk about some additional sampling algorithm, which can be even more useful.